Hi, my name is Nicholas Zhang. I'm from China and I'm the sound designer for an indie game called The Station. The Station is a first person exploration game set on a space station sent to study an alien civilization. It's a very cool little game. Check it out if you haven't. So, in this video, I'm going to talk about the audio obstruction system in the station, which is basically this. And I'm going to show you how to make it in Unity. So, how does something sound when it's coming from the other side of a wall? Just like when your neighbor plays the music too loud, even though the wall can block most of it, the bass still manages to come through. Because the longer the wavelength is, the less it will be scattered or absorbed by the relatively smaller obstacles. And knowing this, many sound designers like to use a low pass filter to simulate the muffled effect. But what if you try to walk around the wall? You'd expect to hear it crystal clear when you finally have no obstacles between you and the sound source. But the process of the sound revealing itself rarely results in a sudden change. The sound becomes more and more clear as it gets less and less blocked. It's a gradual process, right? And the reason is that in real life, you don't just hear sounds from its direct signal. There's also reflections and diffractions during the process of you walking out of the obstruction, even though the direct signal stays almost the same as long as it's still blocked by the same thing. More reflections and diffractions will reach you, therefore, you hear the sound more and more clear. So, how do we simulate this transition with Unity's built-in low-pass filter? Well, we can't really. Sliding the cutoff frequency would be a terrible idea because it would sound like this. Why? Because this part is representing where the obstacle is blocking the higher frequency. It's determined by its material, which is a static property of the obstacle. It doesn't just change its material as soon as you start to walk around it, right? So the sound shouldn't shift like that either. What is changing is more like this part. So in order to make this happen, we can either create a dry wet mixing function for the low pass filter, or more ideally, we can create a high shell filter for ourselves, which is what I did for the station. Let's say we have a high shell filter ready and you can input the Q, the cutoff frequency, and the gain. What's next? How do we control the gain slider based on how much the sound source is revealing to the player? The most instinctual idea would be casting a ray from the emitter to the player and use that ray to detect if the sound is obstructed. But how do we model the diffraction and the reflection? Well, we don't, because there's really no easy ways to model them. It would be a way bigger project to simulate the full audio propagation, and the bigger companies like Microsoft or Audio Kinetic are already coming up with solutions to that, which is not the goal of this video. The goal here is to achieve something similar but simple and easy to use without going down that rabbit hole. So instead of simulating how sounds actually propagate, we can simulate how much the sound is revealing to the player on the perceptual level. As the rate between the sound source and the player gets near a clear path, the sound should already start becoming less muffled before the player can actually see the sound source. That's almost like the player has a hearing zone around them. It means as if the sound source doesn't just cast a single ray to the player, it also casts its many rays around the player. How much the sound is muffled is determined by how many rays cast to that zone are blocked. The more rays we allow the sound to cast, the more accurate sounding we get. But recast in Unity can be very expensive. We can't really afford to cast too many arrays at the same time. What we can afford is to trying to cast one random ray at a time and store the value of whether it's blocked or not. We accumulate the results in an array until it reaches a certain size. Then we overwrite the old data with the new data starting from the bottom of the array. We keep this process going as long as the emitter is within the audible range for the player. Then we will have a percentage of the obstruction level at any given point. If we do this fast enough, we'll probably get the similar desired result as if we're casting many rays around the player. So that's the basic idea of the audio obstruction system in the station. It's not perfect, but it really works in the game. And if you're still interested, I'm going to show you some of the code, which is written in C sharp. I'm not going to show or explain the entire script, not because I think this is the top secret that no one else can know. It's because I want to make this video as short as possible without digging into the minor details. But also, after all, I'm not a professional programmer. I wrote it just because I could, but I believe there are always better ways or more efficient ways to do these things. Plus, it's always different from game to game, right? Let's say if you're making a multiplayer first person shooter, then the scripts will probably need some heavy adjustments. So, I'm only going to show you some of the core parts that are my solutions to the problems occurred to me. You can take away whatever you like from it and make your own audio obstruction system. That's the idea of this video. So the first thing that I'm going to do is to make a high shelf filter in Unity. There are many videos you can find on the internet about how digital filters work in general and the ways to implement them. But basically, if you add a signal to a one sample delayed version of itself, you're gonna get the simplest low pass filter. This is just some quick representation of how filters work in a nutshell, but if you're curious, you can read up more on the FIR and IR filters. Here, what we are trying to implement in Unity is called a biquad filter. The advantage of implementing a biquad filter is that we only need one same formula for various types of filters, including O pass, high pass, low pass, band pass, high shelf, low shelf, and notch filter. The only thing different among them is the calculation for the six coefficients in the formula. And this makes it really easy to program all these filters in one script with the option to switch to whatever filter type we want. Do I need the other filters other than high shelf in this case? No, but it's just good to have all of them. There is a very popular TXT document that everyone passes around when it comes to designing a biquad filter. It's called Cookbook Formulae for Audio EQ Biquad Filter Coefficients, written by Robert Bristol Johnson. It has everything you need to know about the implementation formula and the calculation of the coefficients. The link is posted in the video description. The basic structure to implement a biquad filter in code is like this, where the B0, B1, B2, A0, A1, and A2 are the coefficients. B0 and A0 need to start as 1 instead of 0. And their values are all subject to the filter's Q, cutoff frequency, and gain, which I guess are the only three values that we sound designers care about. How we can calculate the six coefficients from these three values can all be found in the TXT doc that I just mentioned. Here I use the switch statement to switch the calculations depending on what type of filter we want it to be. The default is set to be the high shelf filter because that's the filter we're going to use later. For the audio obstruction to sound good, we want the value of gain's changing speed to match up with the physics in Unity. So here I put all the calculations that involve the gain value in the fixed update function for the best accuracy. In this case, the Q and the frequency values don't need to be updated at all once I set them up, but I still put them in update just in case I want to do something with it in real time. The ZB1, ZB2, ZA1, and ZA2 are the delayed samples. ZB1 and ZB2 are delayed input samples, and the other two are delayed output samples. As shown in the code, because the computer can only process one sample at a time, the way we delay the samples is just store them after we have processed each one sample. The ZB1 becomes the next ZB2, and the most recent input sample becomes the ZB1, so forth and so on. Now we just need to implement this structure using Unity's onAudioFilter read function, which runs on an independent audio thread. the code is the same thing, except we change the sample in and sample out to this data parameter. But you can't just use it like this because this will only work if we have only one channel, which is very rare to see unless you're doing mobile. If we're making a PC game or a console game, we need to make it work no matter if the game is in mono, stereo, or surround, right? So once we get more than two channels, an audio filter read function is going to take turns to process each channel. So what we need to do is just to store the delayed samples for each channel individually. So I made a struct dedicated for storing the delayed samples. Then we declare it as an array in the class so that we can have multiple of them assigned to each channel respectively. Now, in the for loop, I use the modulus operator to get which channel we're dealing with. Then I find the corresponding delayed samples and use them to do the calculation. Then finally, I store the new values back to them. So the filter is almost complete, but I just want to add one more thing to it. I want the filter to be able to control the volume of the sound because I don't want to use the volume slider on Unity's audio source component. It's just bad and you want it to stay independent whenever you can, right? It's super easy though. Just add a coefficient ranging from 0 to 1 to time with the output sample before you really output it. Some may like to do a dB conversion as well, but I'm comfortable with 0 to 1 in this case. Now that I have my high shot filter ready, I just need to make the obstruction script that handles all the raycasting. So the script has five parts. The first part is just checking if the player is within the emitter's range. If the player is out of the range, then there's no point to execute the code. So it disables the filter as well and also checks less frequently to save some CPU. Once the player is within the range, it enables the filter and ray generator function starts to cast the rays. Then the detection function collects all the information that the rays return and calculate the rough obstruction level. Finally, the obstruction function takes over and makes the filter's gain and volume interpolate to the target value. The initialization function is just to make sure the player doesn't hear the sound until the filter has fully filtered the sound so that the player doesn't experience any unexpected or drastic change. The ray generator function actually casts three rays at a time. There's one directly cast to the player. Let's call it the central ray. There's one from a random point around the emitter to a random point around the player. And there's one from that random point around the player to the player itself. The central ray is pretty easy to understand. I will explain the other two rays. Like I mentioned earlier, what we do here is to create a hearing zone for the player. So why do we need a ray cast from a random point around the emitter? Because bigger objects are more difficult to be blocked. You don't want to hear the sound still heavily muffled while already seeing almost half of the thing, right? So we don't just need a zone for the player, we need a zone for the emitter too. And the rays are cast from that zone if that makes sense. Here I use random.inside unit sphere to randomly generate a point from that sphere zone. The zone size is defined by the sound designer. We could just grab the minimum distance from the attached audio source, but that's usually not ideal. You may want the zone size to be different for lots of reasons. A random point around the player is generated in the same way, except it's not a sphere. It's a hemisphere where the player always faces the top of the hemisphere. This hemisphere is the player's hearing zone. The reason why we don't include the other half is because you don't want the sound to be more muffled just because a wall is behind the player. Well, if anything, the wall right behind you should enhance the early reflections, thus you hear things even louder, not the other way around. Also, I made the hemisphere size scaled with the distance between the source and the player, because usually the further you're standing from the source, the relatively smaller the obstacle becomes and the more ways the sound has to reach you. The random point around the player also casts its array to the player itself, because if there's a wall in between, it should be taken into account too. Imagine if there's a wall on the right side of the player, and a point is randomly generated on the other side of the wall, and it connects to the emitter placed on the other side. It makes no sense if that array is considered an open path, right? That's why we need this second array to double check. Now that we have all the arrays, how do we use the information that the arrays return? Let's say we have cast 50 arrays in 1 second and 40 of them get blocked by a wall. Then we can say the obstruction level is 80% in that second. As all the rays are randomly cast, maybe in the next second, only 35 of them get blocked. Then the obstruction level is 70% in that second. But we don't want the number to jump around like that from second to second. We want that percentage number to change as soon as a new ray has been cast. If 40 out of 50 rays are showing blocked, then when the 51st ray is cast, we want to update the percentage immediately whether it shows blocked or not. But we also don't want to keep the divisor increasing to infinity because that will make the percentage harder and harder to change. So what we want is an array of certain size that holds all the raycast values that's used to calculate the percentage. 1 means blocked and 0 means not blocked. Once the last number of the array has been filled, the next value will override the first one in the array and then the next one, then the next one until it reaches the last one, then it goes back to the first one again. This way, we'll have a percentage number that's constantly being updated. You want the size of an array to be large because you want the percentage to be stable and accurate. But you don't want the size to be too large because then it might take too long to change. I leave that number to be set up in Inspector, but I find that around 50 is really nice, and that's my default value for the size of the array. Even so, it can still feel a little bit slow in practice, especially when you go from not seeing the emitter to seeing it or the other way around, because you'd expect the sound changes immediately the second you see it or not see it, as that means whether the direct energy is blocked or not. But it always takes a while for the array to be filled up with new data. So I solved that by introducing a user-defined threshold that can override the target percentage when there's a shift inside until the actual percentage reaches a higher or lower number. That means as soon as the central array detects the obstruction, instead of waiting for the percentage to slowly adds up, this code will force the percentage to be a number instantly until it becomes more. The obstruction function is relatively simple. I just take the percentage and let the actual obstruction level interpolate to that percentage. The obstruction level directly controls the volume and the gain value on the filter, so it needs to be as smooth as possible. But meanwhile, you also want it to interpolate as fast as possible so that the player doesn't feel the latency. I solved this problem by making the lerp speed related to the player speed. When the player stands still, any drastic change in the obstruction level will be noticed right away. So that's when you want the obstruction level to slowly change to its target level. When the player starts to move, however, you want the obstruction level to change rapidly so that it stays in sync with the visuals. And even if the number jumps a bit when it's not supposed to, the player can't really notice that as soon as start moving. In the code, I also set up around 1 second for the obstruction level to catch up with the most recent percentage before it slows down. That's because there's always a very short period of time for the camera to settle down after the player decides to stop moving. This period of time should scale with the size of the array. The initialization function is just to make the sound fit in after the array has been filled up with the first round. But this is only needed for a long clip. If you want to apply the obstruction to a short clip, like a flying bullet, for example, you probably want to rework this part. So there you go. That's the audio obstruction system in the station. It works well for a game like that, but I see a lot of room for improvements if you want to use it for, say, a first person shooter game, where it's important to know people's positions from sound. The doorways can be taken into account, and the obstruction effect can apply to left and right channels respectively, as the sound's clear path could be only on one side. Things like that. Anyway, I hope that was helpful. As much as we all love middlewares, we don't always get to use them. And sometimes creating tools for ourselves can be nice too. Also, shout out to the programmer Ben Suo and my audio director Duncan Walt. The station has a wonderful audio experience thanks to them. If you have any questions or comments, you can send me an email. I'd like to hear from you. Cheers.